Zoom to begin. I'll close this door so I don't wake everybody sleeping in their office. Here we go. Admit. All right. How's everybody doing? Today is Tuesday, the 15th of September of 2020, and I'm Chase Matheson. Today we're going to be talking more about the quotient rule, and then we're going to talk about higher order derivatives, which are just derivatives, but multiple ones, okay? And then if we have time, we're going to talk about the chain rule today. I don't think we're going to have time, but I can dream. So, so a few announcements. Homework 4 is going to be due Monday at 11:59 p.m. So start early on it. Yeah, make sure you know how to do it. No class on Thursday. Okay, so nobody's meeting at any time on Thursday. I'll try to post a review for an exam next week. I'm anticipating, again, having an exam on Friday of next week, which is September the 25th. So I'll post a review with everything that I want you to be able to do on the exam, hopefully by Thursday. So are there any questions about any of these things before we move on? Okay. So last time we talked about the quotient rule, which says if I'm trying to take the derivative of a quotient of two functions, so we're going to say f of x and g of x are differentiable, then the derivative of this quotient of things, well, remember, we call this high and we call this low. Then the derivative of the quotient f divided by g of x is equal to low d high, so g of x, f prime of x, minus high d low, f of x, g prime of x, over the square of what's below. It rhymes, it's so cute. And this holds as long as g of x is not equal to 0. I can't divide by 0, so the original function f of x over g of x isn't defined when g of x is 0, so it doesn't make sense to talk about its derivative at 0. Okay? Or when g is 0, rather. So we did several examples last time. We're going to do a few review examples today. Today we're going to compute the derivatives of the following functions. Admit. Okay, so compute the derivatives of the following functions. F of x is equal to the cotangent of x. And if you don't remember, the cotangent of x is 1 over the tangent of x, which is also equal to cosine of x over sine of x. Okay, so we're going to find this derivative. Then we're going to find the derivative with respect to theta. I realized someone asked me in office hours, there was a homework problem with t's instead of theta, or instead of x's. I've only been using x's, but the independent variable can be anything we want, and nothing changes as far as the mechanics of differentiation. Okay, so we're going to find the derivative with respect to theta of the secant of theta, and this is, well, let me show the rest. So this, again, this is going to be cosine of x over sine of x for number 1. Secant of theta, that's defined as 1 over cosine of theta, and cosecant of t, well, this is 1 over the sine of t. So we're going to compute the derivatives of these functions with respect to the independent variable. So like I said, there's nothing special. I mean, I've been using x's, but there's nothing special about an x. You can use a t or a z or anything for the independent variable. And everything we have done follows in exactly the same way. Okay. So let's look at computing the derivative 1 of cotangent of x with respect to x. Okay, so I'm taking the derivative with respect to x of cosine of x over sine of x. All right, so cosine of x divided by sine of x, that tells me that I need to use the quotient rule, right? When I read this function out loud, I have to say divided by, and so I need to use a quotient rule when I'm differentiating. So what is the derivative here? So this is high, and this is low. Okay, so what's the derivative of this function, cosine of x over sine of x? Yep, good start. Low times. Perfect. And how'd you get that? What's negative sine of x? Perfect, perfect. Times negative sine of x, because that's the derivative of cosine of x. Okay, then minus, so there's low d high. What's next? Cosine of x, so there's high times so we did low d high, now we're doing minus high d low, right? So what's the derivative of sine of x?
Cosine of x?
Perfect, cosine of x. Over the square of what's below. So just sine squared x is how we will write that. The square of what's below. Okay. Are there any questions on that so far? Technically, you're done. If you're on an exam and you're running out of time and you left this as an answer, I would give you probably most, if not all of the points, because technically you've taken the derivative correctly at this point. I would prefer if you simplified this, because there's some trig identities we can use to simplify this. So this is equal to, well, sine of x times negative sine of x, that's negative sine squared x, right? And then minus cosine of x times cosine of x, well, that's minus cosine squared x. And then I divide by sine squared x still. All right, so then the top, each term has a negative, right? I'm going to pull that negative out from both terms. And when I do that, this is equal to, let me zoom in a little, zoom, enhance, negative sine squared x plus cosine squared x, all divided by sine squared x. And what is sine squared x plus cosine squared x?
A 1?
That's 1, perfect. That's exactly right. So this is equal to 1 over sine squared x. Sorry, negative 1 over sine squared x. That's that negative I pulled out in front. And another way to rewrite this is negative 1 over, or sorry, not negative 1 over, just negative cosecant squared x. Okay. Because 1 over sine of x is the cosecant of x by definition. So 1 over sine squared x, well, that's 1 over sine of x times 1 over sine of x, which is just cosecant squared x. Okay, so I mentioned before that when you're taking the derivative of any trig function that starts with the letter C, you're going to have a negative out in front, and that holds here. The derivative of the cotangent of x with respect to x is negative cosecant squared x. Whereas the derivative of tangent of x we found the other day was secant squared x. There's no negative. Okay, so this is just it's not some magic about the letter C, but it's a fun way to remember that if you take the derivative of a trig function that starts with the letter C, you need to put a negative in front of it. Okay. All right, so let's look at finding the derivative 2. We're looking at the derivative with respect to theta of something, and that something is secant of theta. All right. Well, how am I going to do this one? How is this related? I'm doing a review of the quotient rule here. How is this related to the quotient rule? Perfect. Yeah, we're looking at, this is the same thing as d theta, the derivative with respect to theta of 1 divided by cosine of theta. All right. So my high here is just 1. Really, I already sort of showed you guys a rule to deal with this. If you remember, before I proved the quotient rule, I proved a simpler form that looked like this, just 1 over a function. But we'll go ahead and use the full quotient rule here to do this problem. So here we have high is just 1, and low is cosine of theta. So I'm taking the derivative. So when I take the derivative with respect to theta, I'm going to get what? This is a quotient. So I'm going to get what? Well, what's first in the quotient rule?
Isn't it low d high?
Yeah. So low, and be careful, we're not just going to get a 1. We're going to get times d high. What's the derivative of high? 0. Perfect, because 1 is a constant. And this is where people, we might learn it today. We might learn it, we'll probably learn it Friday. When we learn the chain rule, a lot of people mess this up. So be careful when you're using the quotient rule on this. The derivative of 1 is 0, okay? So I get low d high minus high, so that one is just 1, times, what's the derivative of cosine of theta? Negative sine theta. Perfect. Over the square of what's below. Okay, so the 0 times cosine theta goes away. I'm left with, sorry, over the square of what's below. Thank you, Chase, for noticing that. I'm Chase. All right, so this is equal to, the negative cancels there, so I'm left with sine of theta over cosine squared theta. And the way people typically write this is they break this up into sine of theta over cosine of theta times 1 over cosine of theta. And then they write this as tangent of theta times secant of theta. This is the way most people usually write this derivative. But if you went through and you wrote it like that, that would also be fine. So are there any questions about using the quotient rule here? Really, the only kind of trick was remembering the derivative of 1 is 0 here. So that just goes away. All right, let's look at one more. And then we'll know the derivatives of all of our trig functions. Okay, so we want to look at the derivative with respect to t of cosecant of t. Well, again, I'm relating to this to the quotient rule. So this is the derivative with respect to t of 1 over sine of t, right? Okay, so again, we have a high of what? What's our numerator? Yeah, our numerator is just 1. Our high is just 1. And what is our low? Good, sine of t. All right, so now the derivative with respect to t is then equal to, well, what does the quotient rule tell me? What was it? Careful, you don't want to switch them. I think it's low d high, right? Low d high minus high d low. But this one actually, when you do the d high, it's gonna actually go away. So, but anyway, low is gonna give me sine of t, and then times d high 0, then minus high, so 1. D low, what's D low here? So low is sine of t, careful. So D low, cosine of t, perfect. Cosine of t over the square of what is below. Low d high minus high d low over the square of what's below. Okay, so once again, we get, that goes away, and we're left with just negative cosine of t over sine squared t. And again, if you left your answer like this on an exam, that would be fine. You've done enough simplifying. Most people typically write this as, they break it up again into cosine of t over sine of t times 1 over sine of t, which gives you negative cosecant, or well, I'll write it in order. Negative cotangent t times cosecant of t. Any questions on these examples? All right, so now you know the derivatives of all your trig functions. It's a big day. All right, so now we're going to talk a little bit about higher order derivatives. Okay, so when we're taking a derivative of a function, I'll call it f of x, then we know that f prime, the derivative, is also a function of x, right? Well, so I started with a function of x, and I said I take a derivative and I get another function of x. Well, now I can just take another derivative, right? There's nothing special about this first function, in theory. There could be. But the natural question that arises is if I have another function of x, can I take another derivative? And if you can, then you call that second derivative, you call it f double prime of x, or simply just the second derivative of f with respect to x. Okay? And that itself is another function of x. So then the next natural question that arises is, well, now can I take another derivative? And in general, as long as you keep looking at the limit definition, which we won't actually do that, as long as you can use these rules that we've been talking about to keep taking derivatives, then you can take as many derivatives as you want, and you just call, if you take n derivatives, you just call that new function that you get the nth derivative of f with respect to x. Okay, so, and you, oh, excellent question. So yeah, that's a perfect question. I've got an example locked and loaded. for you. But in general, not in general, mostly in this class because I'm going to ask you to do it. But in general, the second derivative in particular tells you two things. Does anyone in here, is anyone interested in physics? Cool. Yeah, in physics, one of the big equations that you always look at, and a lot of calculus is, a lot of the examples we look at is based on this, is F equals ma. So an acceleration is actually the second derivative of a position function. Before we looked at a position function and just took the first derivative to get velocity, the second derivative actually gives you acceleration. And when you're working with that, then calculus really shines. Yeah, excellent question. So the nth derivative, if you're taking n derivatives, you can either write it as this, I'll highlight it. That's the nth derivative. You could also write it like this, the nth derivative of f with respect to x. Either way. But that means just take the derivative in times, where n is a positive integer. Okay. All right, so some examples, we're going to find the second derivatives of the following functions. All right, so first we're going to find the second derivative of f of x is x to the fifth minus 5x cubed plus 17x squared. And then g of theta is theta times sine of theta, and then h of t is 1 minus t over 1 plus t. Okay, so for number one, well, to find the second derivative, you're always going to have to find the first derivative. Okay, so first, f prime of x is equal to what?
Five x to the 4 minus 15x squared
Yep.
plus 34x.
Yeah, perfect. Everyone said it. That was beautiful. That was a chorus of beautiful mathematics, and I loved it. So, are there any questions on where this first derivative comes from? This is the power rule in combination with the sum and difference rule. We use so often that most of the time I won't even mention it. But it is technically something that we used here to say the derivative of this whole thing is just the derivative of this part plus the derivative of this part plus the derivative of that part. Okay, so power rule in combination with the sum and difference rule. Okay, so there's f prime. So f double prime then of x, that's just me taking the derivative of this function here. Okay, so when I do that, f double prime, well, the derivative of 5x to the fourth, what am I going to get for that?
20x to the third.
20x to the third. And then the derivative of minus 15x squared?
Minus 30x.
Minus 30x. And then, yes, perfect, plus
34.
Wonderful. Any questions on that? So second derivatives, just, it's just another derivative. You're not really learning anything new here as far as taking derivatives. Excellent. All right, let's look at number 2. G of theta. So this is 2. G of theta equals theta sine of theta. I want to take 2 derivatives of this with respect to theta. So first I need g prime of theta. How am I going to find this? I'm taking the derivative of theta times sine of theta. So what rule do I need to use?
The product rule?
Product rule, excellent, because when I read that out loud, I had to say the word times, right? Theta times the sine of theta. So product rule says, well, the tablets are great for the product rule. If I call theta the red part and sine of theta the blue part, then the product rule says, well, first take the derivative of the red part. So what's the derivative of theta with respect to theta? Careful. is 1. Yeah. Yep. 1. So 1. And then we'll leave sine of theta alone. So 1 times sine of theta. And then plus. Then I'll leave the red part alone. So then I'm just left with theta. And now I'll take the derivative of the blue part. So what's the derivative of sine of theta with respect to theta? Yeah, cosine of theta. Excellent. And so writing this all in one color, this is sine of theta plus theta cosine, theta times cosine of theta. Okay, so there's G prime. So now to find G double prime, wow. Oh, okay. Oh man. Notability, the clock on it is, if you look up at the clock, it says it's 9:41, and I thought, that's insane. That can't be right. Anyway, sorry. Continuing. So now I need G double prime of theta. So again, I'm just taking one more derivative. I'm taking a derivative of now this thing with respect to theta. Okay. So when I do this, well, the derivative of sine of theta plus theta times cosine of theta. So the sum I can just deal with separately, right? So what's the derivative of sine of theta?
Cosine theta.
Cosine of theta. Plus, and then how do I take the derivative of theta times cosine of theta?
Just do the product rule again.
Yeah, I need the product rule again. Very good. So again, I'll call theta the red part. I'll call cosine of theta the blue part. Then product rule says take the derivative of the first function, the red function. So derivative of theta with respect to theta is just 1, right? 1. And then I'll take the derivative, or I'll leave the blue part alone. So 1 times cosine of theta. Plus, now I'll leave the first function, the red function, alone. So plus theta times, I'll take the derivative of the blue function. So what's the derivative of cosine of theta with respect to theta? Negative sine theta. Perfect. So we are essentially done. We get cosine, I'm going to get cosine of theta plus a cosine of theta there is going to give me 2 times cosine of theta, and then minus theta times sine of theta. Okay. Do we have any questions on this one? All right, one more. So number 3, we were taking the derivative with respect to t of, I believe it was 1 minus t over 1 plus t. Yeah, come on. 1 minus t divided by 1 plus t. All right, so really I want the second derivative of this. But to get that, I need to take the first derivative. So I'll take the first derivative. What rule do I need to use here when I'm differentiating 1 minus t divided by 1 plus t? Quotient rule, right? So quotient rule, I have a high of 1 minus t and a low of 1 plus t. Okay, so quotient rule says that this is equal to what? Low d high gives me low is 1 plus t. What's d high? Negative 1, perfect. 1 minus t, you take that derivative with respect to t, you get a negative 1. That was wonderful. All right, so there's low d high minus high d low. Well, high is 1 minus t. And d low, what's the derivative of 1 plus t with respect to t?
1.
Positive 1, perfect. So minus that, and then over the square of what's below. So over 1 plus t squared. Okay. So when I do a little bit of simplifying, I'm going to get, I have a negative 1 minus 1 is going to be minus 2. And then negative t plus negative, or sorry, minus negative t is going to be plus t. So that's going to cancel out, right? If you write this out, this is negative 1 minus t minus 1 plus t, all divided by 1 plus t squared. I'll just write it down here. And then this is equal to, again, that minus t cancels with that plus t. I'm just left with negative 2 over 1 plus t squared. Okay. Are we done with the problem? No, I needed to take two derivatives, right? I'm finding the second derivative with respect to t. So now I need to take a derivative with respect to t of that guy. So d dt of negative 2 over 1 plus t squared. And what rule do I need to use here? Quotient rule again. So my low is 1 plus t squared. My high is minus 2. Or if you want, you could pull the minus 2 out in front. Constants just come along for the ride, but it doesn't really matter. But yes, d high is going to be 0 for this one. So low, high. So when I use the quotient rule, I'm going to get, again, low d high. So low 1 plus t squared, d high is 0. Minus high, so minus 2. D low, we don't technically have the tools to deal with 1 plus t squared as it's written right now. How can I take the derivative of 1 plus t, the quantity squared?
Chain rule?
Wow, no. Yeah, but yes, but we're going to learn that at the end of class. Huh? No, not quite. Yeah, right now, as it stands right now, we have to expand this and then take the derivative to get that derivative of the low part. But for those who have, those who know the chain rule already, you could just use the chain rule. But we don't know that yet, okay? So 1 plus t squared, this is 1 plus 2t plus t squared, right? If you FOIL that, that's what you get. So the derivative of 1 plus 2t plus t squared with respect to t, well, the derivative of 1 is 0. The derivative of 2 times t with respect to t, that's just 2. And the derivative of t squared with respect to t, that's 2t, right? Okay, and then over the square of what's below. So I'm going to get 1 plus t, the quantity squared, and then I'm going to square that again. So I'm going to get over 1 plus t to the 4th, right? So that 0 goes away. I'm left with 2 times all that. This becomes a plus. So I'm left with, when I distribute this, 4 plus 4 times t divided by 1 plus t to the 4th.
That just becomes a positive 2 right there.
Yeah, because it was minus negative 2. Yeah, exactly. And if you are sneaky or observant or whatever adjective you want, you can say, oh, if I factor out a 4, I get 1 plus t. And so I can cancel because the 1 plus t is multiplying in the top. and in the bottom. So I can cancel this 1 plus t with one of these in the bottom. And so I'm left with 4 over 1 plus 4 over 1 plus t cubed. Okay. If you didn't see that on an exam or something, you wouldn't lose points. You would get full credit for this, for the answer 4 plus 4t over 1 plus t to the 4th. That's our second derivative, exactly. Yeah, you would stop there. Yeah, ooh, that's a good question. If on an exam I asked for the second derivative and you did this correctly, and then you gave me that, like, you kept going, you would probably lose some points for giving me an answer that yeah, you got to the right answer along the way, but the fact that you didn't recognize that you were at the right answer is a problem, okay? So I wouldn't take off a ton of points, but I would definitely take off at least 1 point if you did something like that, okay? Yeah, excellent question. Are there any other questions on any of these things that we did, taking multiple derivatives? Okay, so, oh, I left myself some more room. So an application of this. We know the first derivative of a position function. So again, that's a function that tells you how far you've traveled or how far something has traveled after some amount of time. If you know we know the first derivative of a position function with respect to time is velocity, okay? And so if s of t is a position function, and we're going to be scientists here and measure s in meters, and if t is measured in seconds, then s prime of t, which is the velocity, the velocity of whatever object we're tracking, that's in meters per second is the units on that. S of t is in meters, s prime of t, which is v of t, is in meters per second. Okay. Well, again, we can then take the derivative of the velocity, as long as it's a smooth velocity. And when we do that, well, when I take a derivative with respect to time of the position function, I get meters, I get the original unit divided by seconds. And the same thing happens when you take the derivative with respect to time of a velocity. When you get meters per second, and then you divide by seconds again. You get meters per second squared, which gives you an acceleration. Okay, you what? That's one application for sure. Yeah. Acceleration due to gravity is. I'm actually going to look at an example right now that uses that. So, but if we write v prime of t equals a of t, which is normally how people write this, because acceleration starts with a, then because v of t is also s prime of t, then that means s double prime of t, the second derivative of the position function with respect to time, is equal to the acceleration. Okay. So here's an example. You throw a ball in the air off a 100-foot tall building with an upward velocity of 40 feet per second. What is the ball's acceleration at t equals 2 seconds? If the height of the ball is given by s of t equals negative 16t squared plus 40t plus 100. This is real. If you did this, this is the exact, not exact. This is an idealized version, but it would be very close to what you would actually get if you threw a ball off the air under all these conditions off the air. If you threw a ball off a building into the air under all these conditions, the ball would roughly follow this path. It would go, it would go up for however many seconds until the parabola reaches a peak, and then it would follow this path down. Okay, so acceleration. Velocity is the first derivative of a position function. Acceleration is the second derivative of a position function. Okay, so all I'm asking here is what is s double prime of 2, right? That's me boiling down the question into math symbols, right? So, well, we can take two derivatives of this polynomial. That's not bad. So what's s prime of t? The derivative with respect to t of s. Negative 32t plus 4t. Excellent. And so this is equal to the velocity, by the way. And again, this is real. If you threw a ball in the air with a velocity of 40 feet per second, and you track how long this experiment was going, this is how fast the ball would be going after t seconds. And it's in feet per second, which is a weird unit to use, but this is real. This is real. All right, so then we want to know the acceleration at time t equals 2. So that's s double prime. First was s double prime of t. Negative 32. And so this is kind of a trick question, but it's not. But s double prime, the acceleration is a constant. And for any physicists in the room, acceleration due to gravity is constant. It's negative 32 feet per second squared, or negative 9.81 meters per second squared. So we would expect this. If I throw a ball in the air, the only force acting on it is gravity. And so the only acceleration I would expect is acceleration due to gravity. Okay, so s double prime of 2 in particular is what? Yeah, just negative 32, right? So it's sort of a trick question, but really not. Constant functions are still functions. You just, whatever you plug in, you get the constant back, right? So the answer is negative 32. There are tons of these projectile, this is called a projectile motion problem. There are tons of great examples that I'm gonna definitely put on exams. Like, how high did the ball go? How fast was it going when it hit the ground? And so on and so on and so on. Okay, so I'll put those on a review. I'll definitely put them in the review so you can see exactly how these types of problems are going to come up. But definitely expect some problems that look similar to this on an exam. Yeah.
What's the like abbreviation? Would it be like feet per second?
Yeah, perfect. Yeah, this is feet per second squared. I am a big fan of using units, and so I probably won't count off if you don't use units, but I do like to use units a lot as a sanity check to make sure what I'm doing makes sense. Okay, so, but yes, s of t, I said we're working with a 100-foot tall building, so we know that s is in feet, and I said t is 2 seconds, so you know the time is seconds. So every time you take a derivative, then that just adds a per second. So when I take a derivative of the position function, well, then velocity is feet per second. And then when I take a derivative of that, then that becomes feet per second, or feet per second squared. Okay, any questions? All right, so should I start it? Let's start it. All right, so we know how to differentiate a ton of functions, but there's a ton more that we don't know how to differentiate. For example, this pretty simple looking function, we don't know how to differentiate that right now. 1 minus x squared to the 1/2. It's like heartbreakingly close to a function we do know how to differentiate. It almost looks like just a power rule derivative, but that 1 minus x squared is throwing everything off. If it was just x squared to the 1/2, we can do that, but we can't do this right now. So the reason we can't do this is a composition of functions. Everything we've dealt with so far has been a simple combination of functions, either adding or subtracting or taking x to a power or taking a product or quotient of functions. But we haven't dealt with something that's taking one function and plugging that into another function. Okay, so this is the type of function we're going to be dealing with when we look at the chain rule. Okay. So we need a special rule to deal with this, and that special rule is the chain rule. And once we know that, everything is going to be able, like, we'll be able to differentiate anything that I throw at you, okay? So well, I'm just going to show you what the chain rule says. I'm not going to start the proof until Friday, I think. But the chain rule says if f is a function of the variable u, and then u itself is also a function of x that we're calling g of x, then if both of those things are differentiable, then, oh, this should have been a y, sorry. Suppose y is equal to f of u. And that's a differentiable function of u. And u is a differentiable function of x that we're calling g of x. Then dy dx, so the derivative of y with respect to x, so there's no x over here explicitly, but u depends on x, okay? Then dy dx, well, this is the easiest way to remember it. I think you take dy du times du dx. So y is a function of u, so just take the derivative of y with respect to u, and then multiply by the derivative of u with respect to x. And the reason this is easy to remember, this isn't actually what happens, but if you think of these both as fractions, if you think of dy du as a fraction, it's not. But if you think of it as a fraction, then these du's sort of cancel out and you're left with dy over dx, right? So that's an easy way to remember it. That's not again, these aren't fractions, so it doesn't actually work that way, but it's useful to help you remember the chain rule. Okay. We can write this in another way. The derivative of f of g of x is equal to, you take the derivative of the outside function, which is f prime, and then you plug in the inside function. So f prime of g of x, and then you multiply by the derivative of the inside function. So I'm going to show you the proof on Friday. It's a proof that's technically not wrong. I'm assuming, I assume one thing. I don't think anyone will care about the assumption that I make. I'll say that. So, but we'll look at the proof on Friday. But before we do that, I want to look at just how can we recognize compositions of functions, because that's going to be very important for using the chain rule. Okay, so I want to write the following functions as a composition of two functions. Okay, so f of x. How would I write f of x is the square root of 1 plus x to the fourth as a composition of two functions? Perfect, yes. So we're gonna say f of x is equal to g of h of x, right? So we have an outside function, g, and it almost, if you always kind of think of it as the outside function and the inside function, you'll very rarely go wrong if you think of it that way. So my outside function, well, it's the thing that looks like it's on the outside is the square root of x, right? So we're going to say g of x is the square root of x. My inside function, well, it's just the stuff inside of the square root. H of x is 1 plus x to the fourth. Okay. And so then then you can see if I take g of h of x, well, that's going to be g is, so this says everywhere I see an x in g, I'm going to plug in h of x. So I'm going to put the square root of 1 plus x to the fourth. I don't really need those parentheses though. and then we get back what f of x is. Okay. So being able to recognize functions as compositions is going to be very, very important for using the chain rule. And so we're going to cover that on Friday. All right. If we have any, do we have any questions about anything? Anybody online? All right. Then as a reminder, no class on Thursday. On Friday, first thing, I'm going to cover the proof of the chain rule, and then we're going to go crazy with the chain rule. Okay. So if you don't have any questions, please wipe down your desk before you head out, and then have a great day. Office hours on
Thank you.
Wednesday, by the way. Huh? Yes. Yeah. You guys are Tuesday, Friday. Thanks, everybody.